So I wanted to do a quick recap. Last time we just started going through this book. I talked a bit about it last time, but basically there's something like 750 problems in this book that I'm going to try to work through over the next couple of years. But the good news is the second half of the book is solutions. So the answers are in there. Sometimes it takes a little work to understand the solution, but the other neat thing, I'm going to stick with part one for today, but I might jump around later on. Part one is about series generally, part two is integration, and then part three is complex variables. And then there's a second volume to this book, but I'll tackle that next year sometime, I assume. So yeah, let's just jump in from the beginning. Last time I had talked about basically problems 1 through 4. One is how many ways can you make change for $1? So if you're able to use like pennies, nickels, dimes, quarters, and $half, how many ways can you, well, if you look at this equation, how many ways can you solve this using natural numbers where n is 100? Now, if you don't know anything, I mean, even if you had a computer do this, you kind of do it the same way. You make a big chart and you're just counting. You're running through cases. Like if there's $2 half, that's one solution. If there's $1 half, that variable is fixed and you just cycle through the rest. So you could do 2 quarters and that's 100 cents. And that's a second case. Or you could have 1 quarter and then you realize you probably have 25 cents left to go. So here's all the ways to produce 25 cents using either 2 dimes or 1 dime or 0 dimes. So it's very methodical. That's the way I did it last time. Now let's see, where am I here? Some stuff I wanted to show you. Number 2 sort of generalizes this and he starts talking about generating functions. He says, let an denote the number of ways, like the number of solutions to that equation for a total of n. And then think about this series where you have like a 0, so that's going to be a 1 because there's only one way to get 0 cents, plus a 1, again, there's only one way to get like 1 penny as a solution. So a1 zeta plus a2 zeta square plus yada yada yada, an zeta to the n, going on. So you get this infinite series, and this is called a generating function, like the way that basically techniques that you use to find these coefficients are helping you to answer questions like this previous one. So his question on number 2 was, this has some closed form, like there's a rational function in zeta that is equal to this, and what would you think it would be? The solution to that, of course, is it's this. It's coming from, I talked about it last time, so I won't really go in detail about it, but it's coming from something like if you had 1 plus zeta squared plus zeta cubed, okay? In a sense, this represents all the pennies. This would be 0 pennies, 1 penny, 2 pennies, 3 pennies, etc. And if I then multiply this by 1 plus zeta to the 5, zeta to the 10, zeta to the 15, yada yada, these are all the nickels. And once you start multiplying these, you're generating different ways to make change. So notice that the order doesn't matter here. If I do this zeta 3 times zeta 5, that's 3 pennies and 1 nickel. And it doesn't happen twice. So in a sense, it's considering combinations, not permutations, the way that this was set up. And then you just keep going. So you do this if you want dimes, you go 1 plus zeta to the 10, zeta to the 20. And it's been a long time since I took combinatorics, but I'm sure this kind of technique was in there. I forget if it's like 4 questions or 6 questions. There's a small number of template questions in combinatorics that are just like these. It's probably what he's doing, is teaching us about generating functions in the first half a dozen questions of this book. So yeah, this first one is a geometric series with zeta as the base. So there's the formula for that. This one's a geometric series with zeta to the 5 as the base. So there's the formula for that. And then 1 over 1 minus zeta to the 10. So you get the idea. It's the product of these. It's going to be 5 of these fractions because I left off the quarters and the half dollars. So you'd normally have 2 more factors here, 2 more infinite series factors that have, this as their rational form expression that represents the series. So, where was I? I think I wanted to tell you. Surely it's here somewhere. Yeah, okay. So I'm still just recapping what we talked about last time. I basically did the first 4 questions last time. But at the end of it, I was like, I was trying to explain. He made a comment in the solution about a relation that the coefficients satisfy. And I was like, well, how do you prove this? There's a couple ways that I kind of alluded to. So I wanted to make that a little more rigorous first thing here today before I move on. So here we go. Before I actually move on, this was number 2. It says, here's your infinite series. What would be its rational function representation? And this is it. That's what I was just talking about. But then I was a little, I guess, annoyed because, like, if you were to, if you were to try and like compute these yourself, so like here, his suggestion for computing A100 now using this generating function, like how are you supposed to actually get the answer using this function? Well, what he said was start expanding them. So like expand this out and see what your coefficient is. So if you do that with just pennies, of course, there's only one way. If you do it with pennies and nickels, you'll see you'll get 21. So I didn't, it is faster the way I did this, but it's not much faster. It's basically the same thing. It's basically still just brute force. I might be a little quicker to recognize when we've already computed something by doing it this way. But I didn't, I'm trying to think, did I have a faster method for this? I guess not. Yeah, I definitely did. What I wanted to show you was this. I see. I made little notes to myself to tell me where to go next, but the notes are lying to me. I conflated 2 different problems, and it's screwing me out now. But okay, this is what I wanted to show you. And I wrote a little Perl script also that would, like, maybe I'll link it later to print these out. But basically there's a relation that these coefficients are going to satisfy as well. In his solution, he says something like, oh, you can make a rectangular table to, here, I'll show you. It is convenient to dispose the coefficients needed for the computation in a rectangular array. And that's what he said. I mean, he tries to say some things here, like for the computation of A100, expand successively these products. So he's saying start with pennies, go to pennies and nickels, go to pennies, nickels, dimes, okay? And it's convenient to dispose the coefficients needed in a rectangular array. I think I know what he's saying now. If you basically just make a row of what the coefficients would be for each case. If you had only pennies, then there's only one way to do it, all the way across the board. And so your first set of coefficients, I'm calling these a sub n, but like sup 1. This is our first row. It's just always 1. If you then add on nickels, what happens is every 5 steps, you get a change in the row, like a change in the coefficients. But there's actually a relation between the two. So like a sub n2 is the same as a sub n1, so that solution's still there. But to this, you're adding a sub n minus 5 in row 2. So the first time you see a change is on 5 cents, where you're going to say like, all right, I'm going to take the previous solution, in this case what I have for 0, like the way that you make a total of 0, and add that to row 1's answer. So here you're getting 1 plus 1 is 2. It's telling you there's 2 ways to make 5 cents using pennies and nickels. And then it stays as 2. And if I wanted to get like this entry, if I want to find out the number of ways to make 10 cents using pennies and nickels, it's coming from the entry in row in cell 5 plus the entry that was previously in the previous row in entry 10. So you're basically getting all the ways that we know to make 5 cents plus a nickel, or you're getting all the old ways to make 10 cents just without a nickel at all. So it's a very organized way to say like, okay, here's the case of n being 0. Here's the case of n being 1 fewer than I currently have. And the sum of those two things will get you the correct answer here. And it actually continues exactly like that. So I think when you see these numbers, it maybe makes total sense. Like, well, if you're at 10 cents and there's 3 ways to get nickels, then when you're at 15, there's going to be 4. You're basically just taking this previous answer and adding 1. And it makes sense that it only shifts every 5 cents because we're dealing with nickels now. So when we add on dimes, it's going to be very similar behavior. Like the first 10 entries are the same, but suddenly when you get to 10, obviously now you can use a dime, so you're going to get 1 extra combination. But I won't babble on too much more about this. This is clearly what he meant for like using a rectangular array to compute the coefficients. So I wrote a script that uses these recursive relations to generate, say, the fifth set of, the fifth row, the ones that involve half dollars. But it depends on all the previous ones, of course. But the relations keep happening the same way. It's like, I don't know if you can see this, but probably not. There you go. There you go. So yeah, I don't expect that I did a fantastic job explaining where that's coming from, but there's a very obvious pattern if you start writing out the coefficients, and that's why he told you to do it like, do it for pennies, then do it for pennies and nickels, then do it for penny, nickel, dime, and you'll start to see there's this recursive relation where, if you're adding 25 cents, then this entry in 25, it's basically subtract 25 to see what you get from this case, and then add the previous row's entry in 25. So you'll get a relation like this one. So that was 1 and 2. And then 3, I mean, that was more than you're expected to do for number 2. But I just like to really understand what he's talking about. 3 says, how many ways can you put stamps in one row on a letter using 2, 4, 6, or 8? This thing never autofocuses unless I tell it to. There you go. 2, 4, 6, or 8. So the total postage was supposed to be 10 cents. However, different arrangement of the same values are also regarded as different. So it's like you have distinct stamps. I might have five 2 cent stamps. Now that I'm thinking about that, you can't actually tell. That's not what I meant. That doesn't make sense. But different arrangements using the same values. So if you had like 244, that's different than 442. That's what he means. So that's a different arrangement of the same values. I was starting to say that we have unique 2 cent stamps or whatever, which is crazy. That's not what he meant. I mean, it's not crazy. You can account for that, but that's not what we're doing. Like what I'm mumbling about right now is if you had like the word balloon and you want to know how many times can you arrange these letters, you don't treat these two L's as different. You have to assume they're the same because I can't distinguish if you swap the two letters. So anyway, the same thing's happening here. If you have 2 2 versus 2 2, well, clearly that's the same arrangement. All right, so back to the story. So this is one that we did talk about last time. And I do have lots of things to show you about it, but it almost might be better to just start from scratch. Actually, here, I'll just sort of jump to the end, okay? In number 4, he's going to talk about a series again, another generating function. He called Bn the number of ways, basically the number of ways that you can sum up to a value total of n, but only using the numbers 1, 2, 3, or 4, which is very similar to this 2, 4, 6, or 8 question that he had. So like we're basically looking for B5. If you want the total to be 10 cents, it's the same as question 4, but with a total of n equal 5. And then he has basically the same question. He says this series would have a closed form rational expression for zeta. What would it be? And so I talked about that last time, but it's basically just another. Let me do a new. We did this one last time, but I think it took me a moment to remember. So this time, do I want the ones there? Oh, you know what? I think this is going to be the whole thing raised to a power. So we basically just have, that's your 1 term, that's your 2 term, this is your 3 term, this is your 4 term. Now if you take this, like this is basically giving me the sums 1, 2, 3, or 4. It tells me there's only one way to do it. So what I'm going to do is take this and raise it to a power like k. And I'm not saying that the sum is k. What I'm saying is we're going to have k terms. This represents k terms. If you multiply this by itself a bunch of times, you'll get various cross terms. And this time we're actually getting permutations. Like you're going to see there's 2 different ways to get the sum of 4. It's 1 times 3 or 3 times 1. It actually shows up twice when you multiply this all out. So I suppose we really just want to look at this infinite series, right? You could start with 0 if you want. 0 would be just the sum of 0. There's only one way, we'll say, to get a sum using these terms, 1, 2, 3, or 4, where the sum is 0. Or if you hate that, you can just put it out front. 1 plus k equals 1 to infinity of these powers, okay? But the powers are zeta 1, zeta 2, zeta 3, zeta squared, zeta cubed, and zeta to the 4th. That goes right here. So hopefully you can understand how you would generalize this if you wanted to compute, the number of ways to get sums where the terms are 5, 7, 9. You would just go zeta to the 5 plus zeta to the 7 plus zeta to the 9. You put that in parentheses, and whatever power you raise it to, that's the number of terms that you get. So this infinite series considers all possible terms, and if we expand it all the way out, the coefficients, we'll call them bk, okay? But those coefficients represent the total number of You know, I was going to say it's the number of partitions of a number, but I might be wrong about that. I'm not sure that partitions take the order into account. So I'll just stick to the script. It represents the number of sums using these terms, 1, 2, 3, 4, where the order matters. Okay? And what's my point? Oh, he wanted a nice closed form rational function that represents the series, right? But now you see that it's a geometric series. So here's the answer. It's 1 over 1 minus, and you put your base there. Awesome, right? Seems cute. How does that actually help you compute these? Well, that's another story, right? So he makes a comment. I'll go ahead and show it to you. In his solution, let's move on. In his solution for number 4, there we go. In his solution for number 4, he does this thing I was just talking about, where you raise the that sum, whatever powers you want to actually use as terms in your sum, go there. But then he raises it to s, meaning this will be sums with s terms. I called it k. He's calling it s, where the order of the terms is taken into account. So you have this infinite series, and therefore this is your answer for if you just want a rational function. And then this is the one little blurb he makes for like, how do you actually use this to get the numbers? For numerical computation, use this relation. Bn equals Bn minus 1 plus Bn minus 2 plus Bn minus 3 plus Bn minus 4, which follows basically two different ways. It follows from the definition, or it follows from the equation that you just wrote down. And that's all he says. And I was like, oh man, how do you... I mean, I kind of alluded to it. I was on the right track, but I just thought it was a little wishy-washy the way I left it. I didn't explain where that relation is coming from, where this recursive relation on the coefficients comes from. So let me explain that. It's really rigorous. He didn't have to say much. His hint was perfect for explaining where it comes from. So I have two different proofs for you. This is true for two different ways. The first thing, just coming from the definition of what the BNs are, take a look at this. B1, there's only one way to get a sum of 1, and it's using one term, the number 1. B2, how many ways can you get a sum of 2? Well, you either have a single term, or you have two ones together. So one term or two term. These first few, we can't use the relation, because the relation is actually, it's funny how I didn't actually write it down here. The relation in this case, the first one we're going to encounter is that B5 is the sum of all the previous, B4, B3, B2, B1. And you'll see that this is true, but big deal, it's true once. It's actually true all the time. In this method, I'm not going to prove it in generality. Like, it's not an induction proof or anything like that. It's really just true, like, by observation if you just glance at this. So let's continue. 3. Sum is 3 using the terms 1, 2, and 3. How many ways could that happen? And again, we still have to sort of do this from scratch. Sorry, I'm just thinking out loud. I was seeing if maybe we could actually just do it right now, but I would keep going. So you got 2 and 1, or 1 and 2. Those are considered different. 3 on its own, and then just three ones. So those are all the ways that you can get a sum of 3. And finally, for a sum of 4, a total of 4, using the terms 1, 2, 3, or 4. These are all the ways. Okay? Now, my point was going to be, how do you know that this relation is true? It happens to be true that if you add these up, you'll get the correct answer. What is it? 1 plus 3 plus 4. So 4 and 4 is 8. And then I think here there's another 7. Oh, did I miscount? 4, 5, 6, 7, 8. How did I get 16? That can't be right. Freaking out here, man. Oh, I miscounted. Okay, good. There's 3. Here's another 4 is 7. There's 7 right there. And then here's the other 8. Okay, so this answer is actually 15 ways. But it's really kind of easy to generate this answer from the previous ones. You just say, like, suppose I want 5. First of all, the relation looks like this because those are the numbers you can add. If you're in this set B4 up here, you're only 1 away from having a sum of 5. So clearly all you have to do is add a 1 to every one of these, and you get all the ways to make a sum of 5. Well, all the ways to make a sum of 5 that have a 1 on the end, a 1 as the last term. Okay? So like this entry right here comes from all the ways to get a sum that are exactly 1 away from what you want. Remember, in general, he said Bn is n minus 1, n minus 2, n minus 3, n minus 4. So like this still would have worked even if we sort of generalized this. We didn't use terms 1, 2, 3, and 4. If we used other numbers, we would produce pretty much the same kind of recursive relation. You'd say the current sum comes from this old sum plus 1, or this old sum plus 2, or this old sum plus 3. Okay? And then, of course, the total is n in each one of those cases. So the same thing's happening here. B5 comes from all the ways you can get a sum of 4, and I just put a 1 on the right. And it's clear that for every one of these, you'll get a sum of 5, but it's also clear going the other direction. For every sum of 5 that ends in a 1, it's necessary that all the previous ones have to be a sum of 4, and so they showed up right here. So it really is an if and only if situation. Like, they're contained in each other. Anyway, so then going on, continuing on, we're pretty much done with this explanation. This was the easy way to see it, that this relation is true. If these are all the ways you can get a sum of 3, if you just tack a 2 on the right-hand side, every one of those will have sum 5. And if these are all the ways that you can get a sum of 2, if you just tack a 3 on the right-hand side, those will be all the ways you can get a sum of 5. And that's about it. This 1 at the end, if you tack on a 4, that's the only way you can have a 4 on the right and have a sum of 5. Now, when I was doing this the other day, I thought of that. That's the first thing I said. But then I was worried because I was like, well, if you have 1, 4, how do you get 4, 1? Like, how do you count that? But we counted it over here. So it's really, I mean, I realize me saying that, like, big whoop. But, like, 1, 4 is different from 4, 1. 4, 1 means there's a 1 on the right side. And that means the previous chunk, the part that's not a 1, is a 4, which you would have counted over here in the 4 column. So anyway, it really is pretty thorough, a good explanation. The other way to see it is from the function, from your thinking of it as this kind of gross looking series. So here's our series. I pulled a 1 out just because you don't have to do that, but here's our series. It's equal to this. And I was trying to show that this relation is true, right? Well, replace Bn with this relation and see if it actually equals Bn again. Consider this series instead and see if it equals this fraction. And it turns out that it does. So you get these coefficients times zeta to the n, right? Yes, here we go. So I have a zeta to the n here, but the zeta to the n doesn't match up with the b sub n minus 1, right? So I factored a single zeta out, clearly, right? And then bn minus 2, that doesn't match up with the n. So I'm going to factor 2 zetas out for that term, for that series. So basically just put these coefficients here, put the relation there that you want to happen, expand it. You've got 4 different series here, and then make the make the exponent, match up. So for b sub n minus 3, which it looks like I didn't bother to write here, but there's a b sub n minus 3 here, b sub n minus 4 here. I just factored 4 times to make that match up. And then the negative ones don't make any sense. Those are just going to be 0. There are 0 ways for you to get a sum of -1 or -2 or -3. So it's okay that these it's okay that these numbers start at 1, and then you plug it in, you get b sub n, or sorry, b sub -1 or b sub -2 or whatever it is. That's fine. They're all just 0. B0, though, is 1. That's kind of important. So the first non-trivial terms that you get are here I can plug in 1, here I could plug in 2, here I could plug in 3, right? But basically, if you do that, you're going to see these. Okay, I just re-indexed. So like on this one, 1 gives you nothing, but starting at n equal 2 gives you something. And what it'll give you is b0 zeta to the 0. When n equals 3, you get b1 zeta to the 1, right? So it's the same exact series we've been looking at. All 4 of these do the same exact thing. When you reindex, you just get 4 more copies of our original function. And in front of the first one is a zeta, in front of the second one is a zeta squared, zeta cubed, zeta to the 4. So it's basically, I did it kind of quick here at the end, but it's this times your old function, which is the same as doing just the function minus 1. But anyway, that's a pretty common thing to happen if, I'll write it down for you again with a simpler power series, just in case you're a little rusty with that. But yeah, it worked out. So this junk equals what I expected it to. Remember, I started at 1 here. This was the beginning of the proof. So I started at 1, and I ended starting at 1, and it got me the same coefficients. Why would you believe me? Because when you multiply zeta plus zeta squared plus zeta cubed plus zeta to the 4, when you multiply that by 1 over 1 minus that junk, it's the same as removing just the number 1 from your... This multiplication shifts it. I'll show you what I mean right now. But when you have a power series, say you have 1 plus x squared, yada, 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 right? We're starting at 0. If I multiply this by x, this is what you get, right? And it's exactly the same as the original, except that we subtracted 1. That's what I was just muttering about a second ago. So over here you would have x to the k plus 1, right? If I plug in 0, we get x. If I plug in k equal 1, you get x squared, etc. But also, this function is 1 over 1 minus x. So if you multiply this, you get x over 1 minus x, which I'm claiming is also that. So either way. So that's the trick that just happened on the previous page. That was the end of the proof. Is just kind of this. This happens a lot, right, with power series. If you scale by the base, it doesn't really change the function very much. Makes it a little smaller, but whatever. It's it's basically like a re-indexing of the original function. And I believe that was all I wanted to talk about from last time. Sorry that took so long. So all right, I'm ready to move on. I don't know. My precious book is getting ink on it. All right. Oh, you know what I forgot to mention? This book is, you can find it on archive.org. If you Google this, you'll find, I mean, I don't know, you're not going to find a PDF necessarily, but somebody posted this on archive.org. But I had to have it, so I had to go buy it. I was not willing to click around on the interwebs. All right, we move on. So that was 1 through 4. And I haven't done these in a long time. I did these last year, but let me move on to our next question. I'm looking at number 5. There we go. 5 says, you own 8 weights. 1, 1, 2, 5, 10, 10, 20, and 50. How many different ways can you weigh 78 grams? Like, how many ways can you compose 78? Replacing one weight by another of the same value counts as a different way. So this is what I was just saying a moment ago, like with the word balloon. I was saying, well, of course, the two L's you can't distinguish. No, now we're distinguishing, okay? It's fucking annoying. So like 5 plus 10 is different than 5 plus the other 10 because you have two different actual objects here that represent 10. Okay, so we are taking that into account now. All sorts of torturous combinatorics here today. But that's what he wants us to do in the first couple pages, is learn how to count. So how many ways can you make 78 grams using these? I'm going to just go ahead and do this by brute force. But if you skim ahead a little bit, he's going to do the same thing, of course. Here's our generating function. He's going to use c as the coefficient this time. I don't know if we're actually going to... I don't know if I'm going to make it all that way, but yeah, if you look ahead just to number 7, this is a more clever way to think about it, right? You have an equation. We're going to be solving for the e's. It's sort of like if you could put a 0 or a 1 here. Yeah, he says it right there. Assume the value is 0 or 1 for the e's. So here's a 1, here's a 1, here's a 2, 5. Here's two different 10s represented by the two different variables E5 or E6. And then E7, again, all these e's could either be a 0 or a 1. And if you can tell me the number of ways that this equals 78, then that would be the solution to number 6. 6 is a special case of, number 7. And this time he's a little more subtle. He doesn't say this is a nice fractional function. He says, write this polynomial as a product. So it doesn't necessarily have a nice closed form like the previous one did. But still, you can think of it as a product, just like we did on the previous examples. All right, so back to the challenge here. 5. Question is, I had these weights 1, 1, 2, 5, 10, 10, 20, 50. How many ways can you... Well, I have to be a little careful with how I phrase this. You're not just making a sum that is 78. These are supposed to be separate objects, and they're distinguishable. So like you got a red 10 and a blue 10, and those are different. Something like that. How many ways can you weigh out 78 grams? So a little comment here. 510 and 510 are different. Does that make any damn sense at all? What I should have done is said like 10 sub 1, 10 sub 2. Okay, my note is useless. Never mind. But the 10s are distinguishable, the 1s are distinguishable. Well, luckily 78 is pretty far away from things, right? Without the 50, I don't think we can do it. Oh, but you know what? We don't actually care about the order. We only care about distinguishable items here, right? So like here you can get 70, or you can do 50 with the two 10s. But that's pretty much it. You're going to need to do one of those just to get to 70. So we can go 50 with two 10s, along with however you get 8. And was he very careful with that? Not super careful. So here's one way to get 8, or using this other one is another way to get 8. And that's about it that I can see. So here's the ways I make 70. Oops, 50 and 20, or 50 and two 10s. I don't think there's another way. You just can't. And then next to that, we want to make 8. And the ways you make 8, I just alluded to the two ways. There's only two ways. It's either 1, 2, 5 or the other 1, 2, 5. I know it's confusing, but there's two different ways. So again, 6 sort of helps explain where he's coming from. The e's can either be 0 or 1. And it's been I don't know, it's been more than 20. It's probably been like 23 years since I did anything like this. I wasn't great at it at the time. I had one class in combinatorics as an undergrad. But anyway, so for 5 in particular, we're trying to solve this equals 78, and you're only allowed to let the e's be 0 or 1. I didn't even finish getting an answer up here, by the way. You're just multiplying. There's 2 ways to get 70, and there's 2 ways to get... So my guess is that there's going to be 4. That would be my instinct. There's 4 ways to get 78 using different 1s and different 10s. Oh, no, that's right. Suddenly I was worried about rearranging the 10s, but that's not the point. If I only use one of them, that would suck. But I don't see that happening. I can't get to 70 without. So he made this one a little bit nicer than he had to, thankfully. So like here it's a little confusing because there's 2 different ways because we have 2 different 1s. All right, so 6. Was 6 the one, does he start talking about the series immediately? He wants you to write it as a product? No. 7 is the one where he starts talking about the product. 6, he has like a little complication in our lives, okay? So let me see if I was right about 4, first of all. I probably screwed that up somehow. Let's take a look. Dave says 4. 4 is correct. I don't know if you can read all this blurry junk, but he calls it C78 is his coefficient because that's his solutions in number 7 were called C. He has a series that he calls C sub n zeta to the n, and so just analogous to the other the number 2 and number 4 or whatever, he calls them C's. But so yeah, 4 is correct for the 78, but that was just a special case. And then in 6, he basically says, what if you can take some away? Like, what if you're weighing 78 grams, yes, but you actually have 2 scales. You have like a pan on the left and the pan on the right, and you're allowed to take away. So what I'm saying is to get to 78, you could put 80 on the right-hand side and just put 2 on the left, and it would balance out to be 78. Right? A little bit of a nightmare. But all that really means is we're now allowed to subtract. How many ways can you get 78 if the weights may be placed on either pan, but we're using the same weights as we used to have in number 5? So how many ways can you weigh 78 if you're allowed to like... and I'll tell you, this is, I should write it here. The EIs can be 0 or 1. That's the positive case that we just looked at. What he's going to say next is if we allow the e's to be negative 1, that'll account for subtraction as well. Right? If you're allowed to like subtract one of these, it's a lot like adding on the other side of the equation. If I put a little equals sign here, equals whatever total you want, say equals n or equals 78. If one of these was minus, that's a lot like just plussing it on the right-hand side. So the CNs are going to correspond. I'm probably really confusing anyone watching this by jumping all over the place. But as soon as I saw this equation, I got all excited because that's how you generalize this question. You can use the same statement, and if you want to let the EIs become negative 1, you'll get a different series. But that'll be handling this number 6 question, is what if you can subtract, basically. What if you put weights in both pans? There's a left pan and a right pan, and you still want to generate 78 total, but you're basically allowing us to put like 80. I don't even have 80. That's confusing. Oh, I do, don't I? I forgot I have two tens here. We have 90. So yeah. So like one way, this is going to be kind of confusing already, but you could have this. There's two different ways to make that happen. That's 80. And then over here I could put a 2, or I could put a 1, 1. And anyway, you can see that balances out to be 78. And there's two different ways to do this. I'm trying to indicate it's a distinct 10. But that's another way to get 80. Yeah, sorry, I was fixated on the 70s. Thought we couldn't get higher, but obviously we can. Um, but I don't see another way to get 80, right? Could we get even higher? We could do 90, but then I don't have enough to subtract down to 78. Luckily enough. So this was clearly his intention, was that here's some ways to make 80, and then here's some ways to subtract on the right hand side. But I only see two ways, and here we had two ways. So again, I get 4. That doesn't seem, that could be true. Everything else is smaller. I definitely need the 50 to get anywhere near it. So I guess I'm getting 4 again. Not quite as confident this time. So we could sum to 80 and subtract 2, two different ways. Or here's another way to sum to 80 and subtract 2, two different ways. I'm getting 4 again. I did that kind of quick, but I don't, the 5 was not involved, but that's okay. No, I think I'm okay. We're going to give it a shot, but I feel stranger now. 5, 6, I'm way off. Yeah, no, I'm off. I'm wrong. He says there's 20 different ways. See that? Number 6. I realize you can barely read it, but yeah, I'm supposed to get 20. So I'm like way off. Oh, wait a minute. Well, we could still do. Yeah, I just don't see it. Like we could always. So I was right about this. I was way off on this. The answer is supposed to be 20. Um, oh, okay. So that's fine that I got these 4, sure. But then you could also do like 50. Uh, I mean, I'm basically trying to produce 70 again and then add the 8. Um, like you could do this. You could put 20 and 10 and then put a 10 over here. And they balance out. Now you're at 70. And then you still need to add a couple more. You still need to add the 5 to 1 or the other 1, right? It's two different ways to make 8. That's what we were talking about before. So I missed these two cases. Actually, what is it? Oh, and these are different 10s, aren't they? So I could have put them in another order. Wow. So I'm immediately getting, here's two ways, and then there's another two ways. Here's another 4, is what I'm saying. Like this 10 is distinct from this 10. We could swap that. You get 2 more ways. So here's 2 ways. And then, I forgot about the 1s, right? No. That's okay. So what else could I do? What if I did, like 6 on this side and 2 on the other? Is that going to work? That doesn't make sense. I'm getting confused now. Yeah, I can't. These are just subtracting. Anyway, I'm somehow still missing like 12 more, but luckily it's so symmetric that um, yeah, 80 minus 2 is the first thing I thought of. Oh, can we get to 83 and then subtract 5? Okay, I didn't notice that. So here was one way, here was another, here's another. You can go, like, get yourself to 80, which we've discussed. There's two different ways to do that. And then, here, I'll come back and count in a second. Um, get yourself to like 82 and subtract, or what is it, 78. So get yourself to 83 and subtract 5. So I could put a 2 and a 1 here, right? And that's 83. And then on the right-hand side, on the other pan, I'll be subtracting. I'll put the 5 over here. Now there's only one way to do that, but there's there's 4 ways for me to do this, because there's 2 different 10s, and there's 2 different 1s. So I have this one way, I could change the 1, that's another way, and then I could change the 10, and that gives me 2 more ways. So I'm getting another 4 just from this layout, right? And I'm still short by like 8 ways. But you know, maybe you're seeing now that it's at least possible, and I'm wasting some time. Let's see. Is there another way to make 78 through subtraction? 70, add 8. We did that already, right? Oh, did I not do... Oh no, I see what I did. Oh, I never did 0. So far I've been using as many weights as I can. I never did like 50 and 20, and then just... So yeah, I totally blanked on like, here's 70, and then add 8. 5, 2, 1, right? So there's one way, right? You could also replace these with 2 10s, and you can also replace the 1 with the other 1. So that's, again, 4 different ways. 1, 2, 3, 4. So there's another 4. Ah, my God, brutal. There's one more I'm missing. um, hmm. Maybe it comes from... I'm probably missing another... I don't know. There's got to be another subtraction that I missed. Well, anticlimactic, since we already know the answer is 20, but... Yeah, before I bail onto more abstract nonsense, let's figure out how I can count this junk. 2 different ways to make 80, and then we subtracted 2. And I don't think I screwed that up. I don't see another way to do that, so we're good there. 50 and 20 is 70. Wait a minute. Oh, I see. That's a 2. Good. Perfect. So there's basically 70, because we... Oh, wait a minute. No, I did that right. I was just worried that I forgot to count the 2 10s. Like, you can swap the 10s. But I did that, apparently. Because I had to add 8 here. I got 2 different ways to do that. So here's one layout, that's 2. And then if you swap the 10s, that's another 2. So I didn't miss anything there. And then I had this clever idea of subtracting 5. Um, we can also subtract 3 or 4 or less. Does that help? Is there a way for me to get, like, could I get 82 and subtract 4? No, I don't see that happening. But it looks like I could get 81 and subtract 3. You see that? Yeah, I didn't do that yet. All right, here we go. Here's 80. You can get that 2 different ways, right? There's 80. And then I'm gonna add 1 to get it to 81. And then over here, I'll subtract 3. And that total is 78. But there's 2 ways to do this, and there's 2 ways to choose the ones. And voila, another 4. Okay, finally we're done counting. This was a bit of a nightmare. This was counting to 78. And I'll just reiterate, what you're doing is, probably a smarter way to think about it. It'd be easier to go through these cases if I had just thought about this equation and said, well, you're only allowed to have a 0 or a 1. And you want this to equal 78. Sorry, this was a more complicated way. So we extended it not just 0 or 1, but 0, 1, or -1. That's what we were just handling here. So we're done with the practical part of just counting. We did a small case, right? We did 78 using these specific numbers. But I want to talk about 7, like where can you go with this? What is this series going to be? Is there a function for it? Of course there is. So let's get into that. So I'm now looking at number 7, I believe, in the book. I should probably put a little bookmark here so I can see. We're looking at 7. It says, well, consider sums of this form. And those are, of course, the same weights that we just talked about. 1, 1, 2, 5, 10. Yeah, you can't read what the hell I'm talking about. There we go. 1, 1, 2, 5, 10, 10, 20, 50, right? And in number 7, he's allowing the coefficients, or the variables really, e sub whatever, is going to be a 0 or a 1. Let Cn be the number of different sums where this equation equals n. And then consider this polynomial. He didn't take an infinite series this time. He stopped at 99. Write this polynomial. It's a polynomial. It's got a finite degree. Write this polynomial as a product. I have a sneaky suspicion that I know what this answer is. I forgot. Was that 7 or 6? It must be 7 because I think 6 was the counting part. Yeah, 6 is the counting. 7 is this thing with the equation. So here I'll rewrite this. E1, E2, 2E3. There's a 5. And there's 2 10s. And there's a 20. And that's about it. We also have a 50 at the end. And so for 7, he's saying the e's are allowed to be a 0 or a 1. Let Cn be the number of solutions to this equation where, this equals n. Oh, sorry, I didn't. Got to refocus here. There we go. Let Cn be the coefficient of some basically polynomial, Cn zeta to the n. And this time we're going to stop at 99 for some reason. I don't quite remember, but I have an instinct about it. I think it's something like this raised to a power, like 99, say. Because like what's happening now is I'm allowing 0 to be an entry and I'm allowing 1 to be an entry. So what happens if this is my instinct, but I need to take a product of these things? Hold on. Okay, I see, I see. What if we did like, there's 0, there's 1, and then next to that I have a different one, right? Because I have two ones. And then I have a 2, and then I have a 5, I guess it was. Does this get us what we want? Like, you see now, when I get zeta cubed, there's two different ways that that occurs. It could be this with a 1 with zeta squared, or it could be 1 with a second zeta with zeta squared. So you're actually counting twice. You're counting, you see what I'm saying? You're counting 2 plus 1 as different from 2 plus the other one. This happens twice here. So that's how you're going to get this redundancy where you get an extra 1. And then you just do the same thing with the other guys. And the reason well, the 1 represents e being 0, and the power, the exponent being 1, represents e being 1. I think it's this junk. No. There's more of them, obviously. You know, we keep going. Zeta to the 10, zeta to the 10, zeta to the 20, and finally zeta to the 50. That's not the answer. I'm just saying, I think you're taking this to 99, this whole chunk. I feel a little strange about that. No, not to 99, right? No, I think I was wrong about that. But it's something like this. We're only allowed to use this once, so I don't need to continue anymore, right? And I don't even need to square it. So like one thing that could happen is you could get this times that, times that, times that, and you just add all the exponents. That's the biggest term you're going to get in this product. And that would represent having ones in every single, every single e, every variable. Or you could let them all be 0, and you get just 1 times 1 times 1 times 1, right? So yeah, when you multiply this out, this should account for every possible combination. But why 99? What was he talking about? Oh, is 99 the sum of all these? Is that all it is? That's why he stopped at 99. This is 90, and that's 99. Yeah, okay, I see. So I'm done. I think this is the answer. He's going to probably write it more concisely like this to the k, where k is an element of your set that he gave you ahead of time. So it could be one of these. Does that make sense? Oops, I missed a friggin' 10. There we go. I realize you don't usually multiply count in a set, but we're doing that here. So there's two ones, there's two tens. This is going to be his answer. So this is that polynomial he was talking about. And again, this is called a generating function. This one's not very pleasant, but what if, how would you keep going? I don't know. You really can't keep going. Because we only stopped at 1. If you allow me to yeah, we don't want to think about that, but if you allow this to be like a 2, how does that change? I guess you just square it. Oh, no. I'd tack on another, whichever ones you're allowing to take on the value 2, they get extra terms inside their factor. Does that make sense? If I allowed you to do a 2 here, then that means here I'm allowed to have zeta to the 4. Anyway, that's not what he wants us to think about. I'm pretty confident in this answer. And that's also why he didn't want you to bother to write down, like, yes, it's some polynomial, but this is a better way to think about it. This is the function that he's describing. Let me look at the answer, because we're done kind of talking about it. I don't know, he did square things. Am I on the wrong? Oh, no, he didn't. He only squared 1 and 10. So I was looking at 7. And he squared this one, which I did as well. There's your 2, there's your 5, there's 2 10s, and then a 20 and a 50. And I thought he was going to write it as a product like this, but he just left it like this. And he doesn't say anything else about that one. So that's all he wanted you to know. No, no crazy comments for us to figure out this time. Now, number 8 says we're going to modify this. There you go. Number 8 says, all right, this time let the e's take on the value -1. Let dn be the coefficient that represents the number of sums where the total is n. So you're still dealing with this equation. You're still setting it equal to n, but now you're letting the ei's take on value -1 as well. How would you modify your answer that we just got? Like, it's still a product. Like, what is this polynomial? See, now he's starting at -99. He's allowing us to have powers of negative powers, which would be like you subtracted a bunch of times. So he's allowing you to have -1, -1, -2. And apparently that's going to correspond to zeta being negative, like a negative exponent, excuse me, not zeta being negative, but zeta being raised to a negative power. So I'm not incredibly clever here. I solved these, I did these first handful of problems a couple years ago. So I remember that it's going to be something like this. That's how you take a negative value. So it's the same trick we just did, but if you want to include subtracting, like if you want to include -1 as an option for the e, you just put it there as a power. And again, when you multiply through, you're going to be, in the exponent, you're going to be getting your sums. So here's 1. I'm going to go ahead and square that because we have 2 1s, right? And then I'm going to have another term like zeta to the -2. So this is accounting for a 1 or a -1 in the e value, E3. And then same kind of story for the 5. It could be a -5, it could be a 0, or it could be +5 that gets contributed to your sum. So when this factor gets multiplied by everything, it either subtracts 5 from your sum, or it adds 0, or it adds 5. And then we do the rest. So again, if you want to learn more about this, this is called a generating function, and it's very much a combinatorics conversation. We had 2 10s, square them both, and we're almost done with this one. Zeta to the -20, or zeta to the 0, or zeta to the 20. Zeta to the -50, was it? Yeah, +1 plus zeta to the 50. I'm like 99% sure that this is the answer for 8. Now the whole point of this is that this can now be written, if you were to multiply this out, it's basically a power series. It is a power series. Well, it's got negative numbers, huh? It might be called a Laurent series or something when you generalize and you can have negative powers, because it's not really, they're not positive powers anymore. So it's not defined for all zeta. Like, it's not defined if zeta equals 0, because you have these divisions like 1 over zeta squared, etc. So you usually start to, the first time I saw that was in complex analysis stuff. So yeah, we do have some negative powers here, but here again, the dn represents the number of solutions to that equation that we wrote at the top. But this time it's where the ei's can be -1 or 1 or 0. I'm absolutely positive that that's the answer, but let's go ahead and see what he has to say about it. he doesn't add anything. He has no further comments. So for number 8, that series is, and it's the product that I just wrote out. So if you want -1 to be a value for your variable, along with 0, along with 1, you just include negative powers. Pretty cool, very generalizable. Does it actually help you solve this? I'm not so sure. Oof, this next one, I don't think I'm going to like it very much. It says generalize the preceding example, replacing the coins, the stamps, or the weights by just values, A1 through AL. So number 9 says generalize the preceding examples. I'm not a big fan. I mean, we already know what to do, right? Like, this is not a very interesting question. I wonder what he wants us to say here. Like, for 7, like the one we just talked about, 7 and 8, all he's saying is we've got E1, A1, E2, A2, yada yada, EL, well, here, EL, AL, and you just do the same thing. This is zeta to the negative A1, yeah, that's right, plus 1 plus zeta to the A1. In fact, now is when you probably want this notation. Let's call this AI and let the i's range from 1 to L. So this would be my answer for, you can go infinity this time, I guess, because I don't know how big the A, really it's the sum of all the A. We could go negative A to A, where A is the sum of the AI's. Something like that would make more sense, maybe. Because this is a polynomial. I don't mean to imply, because this is finite. But whatever. What does he want us to say here? What else changes? The previous examples. Well, so this is pretty much it for 7 and 8. And then the previous examples, like 4 was the one where 4 was the one with sums that use terms 1, 2, 3, or 4. And we're really looking at permutations, basically, because 2 plus 1 is not the same as 1 plus 2. So 4 was the one that looks like this. And we got an answer like this. That was question number 4. And question number 2 was the one with, I guess it was distinct. It was like, I can't remember the setup. Screw it, I'll just look. Oh, the change. Yeah, number 1 was making change. So here it's more like a combination. It's like the order doesn't matter. You're solving this equation. It's like how many integer solutions, or I should say natural number solutions, to like x plus 5y plus 10z. So instead of like pennies, nickels, dimes, he's saying, what if it was A1 and A2 and A3? But I don't know, I'm kind of irritated by this question because it's obvious how it changes. So like here would be A1, and this would be zeta to the A2, and 1 minus zeta to the A3, etc. So again, we could jot that down if you want, but it's not super interesting. This was the answer for number 2. I equals 1 to L, and that would give you an infinite series an zeta n. And this one I didn't talk about, but like 1, 2, 3, I actually talked about it earlier. I was saying I was mumbling under my breath that we could change the terms, that this relation would still work. You know, if you don't want to use terms 1, 2, 3, 4, you could use like 5, 7, 9. I think that's exactly what I said earlier. And you would get the same thing, but with powers 5, 7, 9. So in our case, more general version, you'd have a zeta to the a1, zeta to the a2, etc. This one, ouch. So that would be the closed form version. It comes from us doing, Oh yeah, okay. It comes from this, zeta to the a1 plus zeta to the a2 plus zeta to the a3, however many, right? And you raise this to the number of terms that you want. So if you wanted k terms consisting of terms like a1 or a2 or a3, this is the kind of multiplication you could do out. If you count, like the coefficient when you expand this will be the solution, will be the number of solutions. It'll be the number of sums with k terms. Well, the point is that you don't just stop at k, you sum up as k goes from 0 to whatever, to infinity. All right, I wonder what he has to say. I feel like I'm missing the point on this question, because it's obvious that you can generalize it. So I wonder if he had something to add. No, not really. He doesn't really have anything to add. He did exactly what we just did. So that's good. Good. Here's the answer to 9. Wow, Euler did this back in the day, along with Leipzig and Berlin and Tobner. In 1922, must have written some note about it. And then again, Leipzig and Teubner, I don't know. The change problem, he must have borrowed from this book. So yeah, this was the change problem. I jotted it down here as a product. And the number of non-negative integrals. I was saying natural numbers, but natural numbers along with zeros. Of the Diophantine equation, boom. So the x's are the variables and the a's are the weights that he gave you. And you'd be solving, the number of natural number or zeros. So like x2 could be, all the xi's could be 0 or 1 or 2 or any natural number. The postage stamp problem is really about permutations, because like 1, 2, 3 is not the same as 1, 3, 2. Is not the same as 3, 2, 1. So there's permutations involved there. That's the one where it looks like this. Anyway, this is a cool. These first 10 questions were pretty awesome. It's really teaching you how to count. It's teaching you a lot about generating functions, and it's basically gone through the biggest cases that you would see in combinatorics. And maybe I'll move on. But yeah, it was. I guess I'm not missing anything. I thought that. So the first weighing problem, this was the one where you could only have positive weights. All the weights are on one pan. So you're only adding, and we got this product. I really don't know why he asked us to generalize it, except just to have like one answer, like here's a place we can reference. Now he can say, go look at number 9 whenever he wants to talk about any of those questions. So let's look at number 10. There's going to be a few more here that I'm sure are similar. I've done these before, but I no longer really remember how to do any of these. So we did 8, we did 9. 9 was just a generalization. It was kind of a strange question to me. 10 looks easy. 11 might throw me for a loop. I have a feeling I'm going to be missing some like subtle detail in the phrasing. 10 says an assembly of P people elects a committee. Are we all having flashbacks to discrete math? So number 10, P people to choose from, create a committee of N of them. How many committees can you choose? This is like, this is like finite math 101 stuff. So it's a combination. Like, they didn't suggest that there's a president and a vice president or there's any sort of hierarchy among the committee. We just want a group of people. So this is just P choose N. Not much to say. Maybe we should move on to 11. There are P people sharing N dollars. How many ways can they distribute that money? And then 12 says there's P people sharing N dollars, but they need to each get at least $1. How many ways can you do that? And then 13 is clearly some sort of generalization. 14 is getting away from me, but it looks like it's related. Yeah, I don't know. But yeah, we can go back. We should look at 10 through 12, or really even 10 through 13. I don't remember this, but it's clearly easy. It's something I should remember. 10, obviously, I remember. 10 doesn't take any effort. 10 says you have P people, select N of them. P choose N, this is a pretty common notation for this. You could also do P choose N if you're using the, a lot of people have an NCR button on their calculator for combinations, but P choose N. I want to say, wow, it's been a long time. P is bigger, first of all. Wow. Right. Okay, sorry, I was just, for some reason I was thinking it was supposed to be a fraction, but it's not a fraction, of course. These always work out to be integers. So in this case, this, well, here's my quick explanation. It would take a couple lines to explain, but it's not really that complicated. If you have, say, like 30 people or 10 people or whatever, there's this many ways to arrange them all. I'm dividing by the number of ways to arrange just the N that we selected. And then I also want to, that's the part that actually matters. There you go. So how you would actually explain where this is coming from, again, this is like finite math 101 conversation, but I think of it as tasks. There's something called the multiplication principle, or the counting principle, I suppose. Suppose you wanted to select 5 people from a group of size P. You'd at first you'd have P to choose from. Once you've chosen that person, they're out of the pool. You can no longer select them, so there's one fewer. Then there's one fewer, all the way down to however many you want. A nice way to represent this is to write P factorial, but that goes way too far because it goes all the way down to 1. So we stop at P minus 5 factorial, okay? This will divide the 5 and the 6 and the 7 and all those other lower numbers that we don't want. We just want the top 5. So that chunk right there, I don't know if you can still read this, but that takes care of selecting 5 people from a committee. Now the problem with this answer is that it's ordered. If I select Dave and then Sarah, that's different than selecting Sarah and then Dave. Okay, so this is ordered. This is a permutation. This is actually what I just jotted down here is an example of the NPR button. So this is ordered. And if we don't want that, we divide by the number of people that you selected. So in this case, 5. There would be 5 factorial ways to arrange these in different ways. So if you divide this by 5 factorial, you get a formula. And so this would be an example of like P choose 5 would be P factorial over 5 factorial and P minus 5 factorial. This chunk on the right is just a nice closed form way of writing that you permuted 5 items. And then here's me removing the ordering of those 5 items. Anyway, that was overkill for an explanation for 10. Now on to the part that I don't remember. There's P people sharing share N dollars among among P people. Huh. Wait a minute. Well, no, it's okay. You know what? My instinct is to say we're going to get something like this. You could just give everyone $1. There's this many ways to do that. Or you could select fewer than that number. And there's a bunch of ways to do that. Okay? I think it's this sum all the way down to 1. So like here, this last one, P choose 1 is of course 1, but it's like I chose to put all N dollars into this one person. How many ways could you do that? Well, there's P people to choose from. Oh, did I say 1? I'm sorry. This is actually P. This is P is what I meant to say. P choose 1 is 1. It's P on top divided by 1 factorial. And then finally, do we include this? I don't think so. We're not going to choose 0 people to give the N dollars to. So I guess it's this, right? Either we select N different people, they each get $1, or we select N minus 1, that means one person gets 2. This is, by the way, the same as P choose 1. I don't know if you recall that. He's probably going to have us prove that in a couple pages. Yeah, it's good stuff. This is pretty elementary, right? I'm pretty confident in that answer. So I'm going to move on to 12. It says there are P people. 12 was P people sharing N dollars, but I want each one to get at least $1. How many ways can you do that? That's a little different. There are P people sharing N dollars. I didn't, my issue is here. I sort of assumed N was less than P. It's not a problem if it equals P. But if it's more than P, obviously my formula makes no sense. And I would assume, you can make sense of it. Maybe he's going to answer, maybe he's going to have like a generalized combination formula that he uses. Maybe that is what he wants. Well, we'll see in a moment. Can you just do it twice? Can we just split it into P plus the remainder for N, And then, that's very sloppy. Yeah, we don't want this one, but isn't there a formula for this too? This sum is going to be, I need to just look at what he said in a minute. Anyway, 12 was share N dollars again. Everyone gets at least 1. guess my instinct there is that you're there are P people sharing N dollars, each getting at least $1. How many ways can you do it? Um, I was just anyway. My instinct here is, of course, to just take your N dollars, subtract P, and this is how much you have left. So we're going to sort of repeat what I did a moment ago. You're basically just doing this. That's my answer. Choose which people get the remainder of the money. But again, it's similar to this. I would think it would be like this answer. What are we stopping at? Well, it could be that you gave all the remaining money to one person, and that would be the number of ways to do that. So this would be my answer for 12. Yeah. All right, I better take a look. I'm feeling very weird about this because I also didn't consider if there's like more dollars than people, and it just feels sloppy. What am I talking about? So 10, I don't know, maybe we don't even need to talk about this. I'm showing you answers for 10, 11, 12 now. Yeah, it does some. Yeah, there's a formula for this. He talks about an 11. Was I right, though? Oh, he's got negative powers. Cute. Anyway, so 10 is, of course, him discussing the combination function. So P choose N. No surprise there. Oh, you can't even read it. Here, let me back up. There you go. 10, he's reminding us of some previous problem we did, but it doesn't matter. It's a moot point. It's just combinations. 11, this is equivalent to someone owns quarters minted in P different years. How many different ways can he pay out N quarters? So he's using, notice him referencing 9, his big mega generality question. I'm gonna have to like review this and talk to you guys about it next time. Someone owns quarters in P different years. How many different ways can you pay out N quarters? I mean, that's a fine way to think about it. Although it wasn't a very tough problem to approach anyway. But then he says he starts thinking about problem number 1, where he was counting all the ways to make change. Right. And then it looks like he's Oh, is this the binomial? Yeah, he didn't. Okay, sure. He alluded to it here. He's using the binomial theorem, which he stated in number 10. Um, so he's using this expansion, but with zeta being negative zeta, and that's why you get these powers. What I don't follow, I don't think he meant to put negative p there. That's got to be a typo. I think he just meant p choose 1, etc., p choose n. The negative is not a typo, evidently. It's a product of p separate single term things. He's saying like you either get a dollar or you don't. Like hmm. He's saying we're gonna have p of these. Um, I don't know why. I got to think about it again. Um, so this was the pennies case. Um, yeah, I guess this is another way to think about it. Sure. Hmm. Anyway, this is what he's reminding us of is from problem 1 and 2. Um, oh, yeah, sure. Quarters, whatever, minted in p different years. How many ways can you pay out n quarters or whatever, something like that. Um, so one of these factors is one particular year of quarter, and you could just be all n of them coming from that year. So it would be like zeta to the say 10 times 1 times 1 times 1 for all the other years. Um, but in general, this is you expand this, and you get our series that we were talking about earlier, and a sub n corresponds to your answer. So then he goes about trying to find a formula for a sub n. And he's getting this, which I swear I would have been able to get the same formula. Like, I'm pretty sure this simplifies to be what he's writing here, but he's approaching it differently than I did. But I could be wrong. I mean, this was kind of sloppy. You just add these. These are the same, actually. Never mind. Forget about my answer. I can't remember. I mean, we could just prove it. And then this one's the same kind of thing, but with an n minus 1. Yada yada. Oops, this is not minus 1. It's minus n plus 1. Blah, blah, blah. Yeah, there's a nice formula for that, but I don't quite remember off the top of my head. I see what he's saying, but I don't. First of all, those are not negative p's. I'll see if I can find some errata for this book. Probably not going to, though. These coefficients, though, that makes sense. So he's just Oh, I see why it's negative p. That's not a typo. I'm sorry. This is, he's just using the binomial theorem again, but with a negative exponent. This is correct. There's nothing wrong with what he wrote. This is a generalized combination, you know. He didn't really talk about it up here, but this is true for integer p, not just natural numbers. It makes more sense for natural numbers, but yeah, I forgot. He didn't screw this up. It's not a typo. I just wasn't thinking. Um, hmm. So I'm not going to be able to continue really. He's expanding this with binomial coefficients, and then this is a formula for if you look up. See, this is where I should probably like have a browser up so I can show you guys things. Negative binomial coefficient is what I'm. Eh, eh, nope. Never mind. Not quite finding what I wanted, but if you look up a binomial theorem, in fact, probably even just on Wikipedia, there should be a section with like negative. It's not multinomial, but it is probably under like generalizations or something. I guess I thought it was worse than it is. Yeah, it's just this formula. Yeah, for some reason I thought this would explain it. Yeah, he's not explaining it. He's just saying an is that number, and that number is this. Okay? So he's using some kind of machinery here, but it basically is a generalization of the binomial theorem that he stated right there. So I think I'm going to log for the day. Oh, is he getting into multinomial stuff down here? We'll see. I'm going to take a look at this in my spare time, see if I can remember any better explanations of this. But I'm starting to think he just, like, he thought about it this way, did binomial expansion, and then said, oh, ands of those coefficients. That would be this. So anyway, this is getting to be a long session. I'll try to do 2 or 3 of these a week. I was hoping to do 3 a week, but we shall see. I'm not always going to have something enlightening to tell you. Mostly I'm doing this so that I can stumble through this and show you my struggle. But here's who we have to thank for this. Pólya and Szegő. This photo was taken probably around the time that they wrote this. This is 1925. And this English edition came from 1972, but if you get to the end of the preface, it mentions right here that they wrote this in the fall of 24. They were working together. Yeah. Anyway, thank you all for watching Dave's struggle with analysis. Have a great day. Ta-ta for now. Probably see you again Wednesday or maybe Friday.